It sort of felt like doing logo a little bit.
Yeah, little turtles. So what you guys should do is take turtles and make them move around. Someone said it was like logo. Logo used a little triangle that they called a turtle to draw. Instead, do turtles. I've heard from some people that GIMP is working a lot better than Popcorn for printing. So if you guys want to print out better images to submit for the contest, that would be cool. GIMP doesn't actually reverse the whites into blacks. So you might actually get some better images printed out. I'm not quite sure what happened with Popcorn, but Chris did a lot of work getting the graphics to work for us, so we're not going to say anything about Popcorn. We're happy that we had graphics yesterday. I believe it's GIMP. I've never actually used it myself. Okay. So 2 handouts for today, the next problem set, which is replacing an advisor for freshmen at some mythical university called Burgundy University, maybe down the river somewhere from here, and the lecture notes for today. And today we're going to be going over symbolic data and then looking into symbolic differentiation. So all that stuff you guys learned in month 0, some of it's coming back. So we'll do some differentiation today. Today we're going to see another special form called quote. And I could say quote A. This is the real official special form way of writing it. Nobody ever writes quote for the most part. We would usually write apostrophe A. It's the same thing as quote A. And what quote does is anything after it, after this, so this A here or the A after the quote here, is it doesn't actually evaluate it. It just keeps it as a symbol within scheme. So if I wanted to put my name into a list, well, if I said list Holly like that, I'm going to have a problem. Because scheme is going to try to look to see what this is bound to in the environment. But I don't want it to be transferred to some number. I don't want to define me as a number. So I'm going to put a quote in front of it. So that list quote Holly is going to make a 1-element list where the first element is the symbol Holly. Okay. So you guys actually saw this, I believe it was problem set 3. We talked about in, was it 3, 4? Frames? 4, yesterday. So we had a data structure, and we asked you why we would want to have a 4-element list for a frame where the first element of the list pointed to the symbol frame. Okay, and we saw that it said list, quote frame, and then the other 3 parts. Okay. So in this case, why would we have wanted to have it in that list? To identify its type. Just allows us maybe to do some error checking to make sure that we're actually passing a frame when we're trying to draw a picture. Here, why would I want my name here? Well, maybe you'd like your program to be a little more interactive. Rather than just working with numbers, you could work with some symbol for somebody's name. So let's look at some examples of quote takes one thing after, but you could do something like this. Quote ABC. Okay? So there's only one item after it. What's important to remember about quote is that anything after the quote will not be evaluated. So let's say I had defined some variables, and let me actually use the ones off the handout. I'm going to define A to be 3, and we're going to define B to be 4. Now, if I said list AB, what would be the list that would be returned from that? The list 3, 4. Okay. Now, what if I said list quote A, B? What's that going to be? A4. Now, what if I said quote AB? It's the list of A and B. Okay. Because of the quote here, before our list that we've written, these are not going to be evaluated. Those will be kept as symbols. So this is a nice shorthand for writing a list. If you guys are typing things in, you can do quote, and then in parentheses, you can put your list elements. However, if you want any of those elements to be evaluated, you should be using list, because then you can mix things that are quoted with things that aren't quoted that you'd like to have evaluated, like we did here, list quote A and B. Okay?
That is actually a list, and that the internal representation doesn't look.
This will actually create a box and pointer diagram where the first element is A.
That part actually confuses me a little bit. Why not evaluating it makes it into a list? Does that make any sense? I mean, a list is defined by having the null at the end, and we didn't write any null at the end of the AB in parentheses, or nil, sorry, nil.
Okay. The scheme interpreter just knows that if we're quoting anything in parentheses, it should make it into a list. Okay, so the interpreter is doing that for us automatically. And then any elements within that, it's not going to actually evaluate them, it'll just put them in as symbols. So the scheme interpreter is doing that for us.
And if I did quote list AB, it would be exactly the same, like this. No, if I wrote out quote. Sorry.
Remember, writing out quote and doing the quote is the same thing.
That's exactly the same.
Yep. So what do you want me to write? Quote.
Open parent AB.
Yep. That's going to do the exact same thing. So this is going to return AB. What's that going to return? Quote list AB.
List of list AB. First having your list.
Okay. If I try to then apply that list, is it going to work?
Nope.
What do you guys think? Is that going to work or is that not going to work? If I then say something like, let's say I actually define this to be C. And then what I'm going to do is I'm going to take the car of C and apply it to 1, 2, 3. No. Why not?
The car of C is list. List is now a symbol.
Right. This is now a symbol list. This no longer is the primitive procedure list. It's the symbol list. So actually scheme is going to return an error if we try to do that. Okay, so we need to be careful what we decide to quote and what we're not quoting. So if you want to make a list of multiple procedures, let's say, depending upon if you've got symbols or numbers, you either want to cons them or add them. Okay, you should say list cons plus, because if we shorten that, and if we instead wrote quote cons plus, not really shortening, it's writing it very differently, these are going to be symbols. Whereas when we use list, these are going to be evaluated two procedures. We're going to have a list of two elements in which there are two procedures as each of the elements.
If we tried to if we evaluated the first one, what would it print up on the screen when we evaluated the list construct?
It's going to print out a list, and however procedures are printed, let's say proc, actually probably prim proc, or compound proc, or some sort of proc. So it's going to print a list with two procedure representations within it. And then what we could do is we could say, let's say we define this to be D. Then what we could do is we could say if, let's say we had two numbers. So rather if and number question mark and 1, number question mark and 2, then we're going to apply the catter of D to N1 and 2. Otherwise, we'll apply the car of D to N1, N2. So we can make a list of operators, and then depending upon what we have for values, we could decide which operator to use. Now, we could say, why the heck wouldn't we just write plus and cons there? And in fact, that would be fine. In this case, we haven't really built any nice abstraction barriers up because I'm just using car and catter. But you could imagine we could have something called combine two numbers and combine two symbols. Okay, and that would be nicer. And then combine two numbers would bring addition in, and combine two symbols would pull the catter, the car to get cons. So this is violating any sort of abstraction, really, that we would have. Okay. So, questions so far on quote? Okay. What I would like to talk about are different ways of telling if things are equal in the system. We have some built-in tests for equality. We have EQ, question mark, the equal sign, EQV, and equal. Those are all built into scheme, yes. Okay. So, EQ, this is the most discriminating test we have. And these primitives are described in all sorts of gory detail in the revised report. If you want to look at it, it gives all sorts of examples of when things are going to be each of these classes. So EQ is the most discriminating test of equality. Okay, so if EQ can't tell the difference between two symbols or two things in scheme, nothing else is going to be able to tell the difference between them. Okay, and with EQ, all bets are off with numbers. You should not use EQ on numbers. Okay, because some numbers will be EQ. For example, if we say EQ 1, 1, that will return true. But if you say EQ 1.5, 1.5, it's going to be false. Because there's no guaranteed how numbers are represented internally in scheme. Okay, and we don't know how they're mapped in scheme. And what EQ is looking for is it's saying, are these the same object? Okay. It's looking for it to be the same thing, the same object. Okay? And we don't know in scheme, these numbers may be represented as two different objects, and we don't know in scheme how numbers are represented.
17 may be represented as two different objects.
If we said EQ 17, 17, I actually can't tell you without testing it what our version of scheme is going to do. I'd guess it would go false. EQ only tends to work on very small whole integers with numbers.
Would work, but the others...
It's implementation dependent. It does work in our implementation. I tried it out. But you never want to use EQ with numbers. It's a bad, bad, bad idea because you're going to get all sorts of weird behavior. If you want to test equality of numbers, we're going to use equal sign. And that's going to give us what we expect when we're testing if two numbers equal. So if we were to say equal 1.5, 1.5, it would return true. That's what you expect with equality with numbers. EQ is not going to provide that for you.
EQ test to see if they're the same object. Is that?
Yeah, I'm just going to talk about that. Once I give the definitions, I'm going to give a bunch of examples. EQV could be considered the usual test, although I doubt for equality. Okay, so this uses EQ for symbols and Booleans and it uses equal for numbers, the equal sign rather, and it uses string equal question mark for strings, and then it uses EQ for pairs. And this is where we're going to start to see that there's differences between EQ, EQV, and equal. When we're looking for EQ for pairs, and I'm going to put some examples of this up on the board once I define equal. When we use EQ for pairs, we're looking for the same box and pointer diagram. If we create two different box and pointer diagrams, they are not EQ. And we'll go over that in a bit. Equal is going to test if two things are the same. And generally, we say that they are equal, question mark, if they print the same. So in some sense, equal is our least discriminating test. So what it's going to do is it's going to use EQV to test non-pairs or single items. And then if there's any sort of list structure, for lists, it recurses on the car and the cooter using equal. So let's look at some examples where these things go awry.
If the list includes numbers, why should EQ question mark not make mistakes if it goes on numbers?
Because it's not using EQ for numbers. EQV, if it has numbers, is using the equal sign.
But EQ question mark is used for pairs. If the pairs is pair of numbers.
Yes, but if we get to a pair, well, let's just actually look at some. So let's look at a few examples. Let me define three lists. These are also on today's handout on page 2. Define A2 to be the list 1, 2, 3. And define B to also be the list 1, 2, 3. And I'm going to define C to be A. Before we start talking about any of these equality tests, let's draw the box and pointer diagrams. A is a list of 3 elements. The first element is 1, the second element is 2, the third is 3. And then we have a binding of A to that box and pointer diagram. And I simply make a binding to this list A. No. When we say B is the list 1, 2, 3, a new box and pointer diagram is constructed. So we're going to get a second box and pointer diagram that's going to look an awful lot like the first one. But internally in Scheme, these actually are 2 different objects. And B will be bound to that second list 1, 2, 3. Finally, we define C to be A. That's going to make a binding from C to whatever A evaluates to. So we have a binding C also pointing to that first list 1, 2, 3. So EQ. It's looking to see if 2 things are the same object. Is this list the same object as that list? No. It is not. And Scheme will return false. Okay. How about EQ AC. Well, C and A are both bound to the same object, the same box and pointer diagram. So that's going to be true. So now we're going to look at EQV on A and B. And let's look back at the definition of EQV. It says we're going to use EQ for symbols and booleans, equal for number, string equal for string, and we're going to use EQ for pairs. So if we're going to use EQ on pairs, are A and B going to be EQV? No, they're not. But will A and C be EQV? If something passes EQ as a test, it's going to pass EQV and equal. If it passes equal, we know nothing about whether it's going to pass EQV or EQ. Okay, so it goes one direction, not the other. Now, are A and B equal? Yes, because what's going to happen here is we're going to use EQV for our primitives, not for primitives, for the atoms, for the non-pairs. But when we've got a list, when we've got a box and pointer diagram, we're just going to call equal on the car and the cooter. So we're not looking to see if we have the same box and pointer structure. All we're looking to see is, are the elements within the list the same? Okay? Now recall that when it's checking to see if these elements are the same, it's using EQV. So if we had numbers, it would be using equal for the numbers.
Say if we had, instead of the 3, say we had some symbol there. You show that EQV uses EQ for symbols. Are they the same symbols, even though they're in different lists? Would equal still return true?
So what you're asking is,
In a list 1, 2, Holly.
okay, let's go for even the simpler case. EQ quote A. Is that going to be equal? That is going to be. The two symbols are the same. So in some sense, you could say, well, why would the two numbers be different, but the symbols would be the same? And scheme is going to represent these two symbols. This would be the same representation, whereas in numbers, we just don't know how numbers are represented. So these two symbols will actually, that will return EQ for us.
Because they're pointing to the same object, they're stored in the same.
There's only ever one instance of a symbol, of any given symbol.
So we had said A and B are going to be equal. Yes? No? Maybe? And then, oh, this is a no-brainer. Since we already know that they were EQV and EQ, they'll also be equal. So these are different tests for equality. And the real key to using these is, do you want to be able to differentiate box and pointer structure or not? Do you care if it's pointing to the same list or the same console, or do you only care that it looks the same? So you can think of, we were doing the other day, we were using consoles to make rational numbers. So let's say we define my favorite 1/2 as a make rat of 1 and 2. Now, let's say I want to define another rational called 50%, but represented as the rational 1, 2. Now, if I wanted to see if those two rats were the same, what test would I probably use? What test would I want to use? Equal. The full-out equal. Because if I'm testing to see, in this case, whether two rationals are equal, I don't care that there's one console like this, 1, 2, pointed to by, rather bound to 1/2, and then another one called 50%, bound to a second console with 1, 2. Okay, so if I'm testing for equality in that case, all I care is that they both have 1 and 2, a con cell with 1 and 2. Okay, so in that case, I don't care that they're the same object.
The reason that these box and cell diagrams are different is that A is different than B.
The reason that they're different, well, the reason that they're different really comes in more of this evaluation here. We're binding A to be the evaluation of that and B to be the evaluation of that. And when we evaluate list, we create a box and pointer diagram. And Scheme actually has some internal representation for representing lists like this, so that it creates a box and pointer diagram or something like it within Scheme for this list 1, 2, 3. When we come down to this list 1, 2, 3, Scheme doesn't say anything like, oh, let me see if I've built anything like that before and try to reuse. It says, you want me to make the list 1, 2, 3? No problem. I'll make the list 1, 2, 3. And it makes a second copy of it. Okay. And this is a good thing. Yes, let me ask the question first.
Suppose we had two objects that contain equivalent values, but their structure was different, such as a pair 1, 2 on the one hand and a list 1, 2 on the other. If we compared those using equal, what would we get?
Okay, let's look at that. So let's say we have 2 items, x defined to be a cons 1, 2, and then we're going to define y to be the list 1, 2. That means we have x is bound to a con cell 1, 2, and y is going to be a list of 2 elements 1, 2. Okay. So what happens if we say equal xy? Well, the structure is different, okay? Because what's going to happen is we're going to recurse on the car, no problem there. But then we're going to recurse on the cdr. And the cdr of x is the number 2. But the cdr of y is the list 2. And at that point, it's going to return a false. Okay. So we do care about the same structure, but what we don't care about is if it's the exact same physical box and pointer diagram. That is, where we've got A and C pointing to the same box and pointer diagram. And here we've got a second different one. They look the same structure-wise, but they're 2 separate objects within Scheme. Okay. Yes?
Do any of these test equivalence of procedures?
Goodness. Procedures.
The same procedure with 2 different names, or different procedures with the same name.
Certainly it's going to work with equal and EQ, EQV, equal on procedures. I happen to bring my handy-dandy copy with me today.
My bet is that EQ is the only one that's going to work at all the way you would think it's going to. Only if they're the same object.
Yeah, but if EQ works, then they all work.
Or that.
Right, but it's not going to give you, if you write 2 procedures which have the equivalent
Structure. Yeah, it's not going to go into the procedure. So this will tell you if it's the same object, right? So if you're looking to see if you've defined, let's say we define z to be plus, then we could say EQZ plus, and that's going to give us what we expect. Now, if we did something like EQ lambda XX, lambda XX, I'm not sure. John's reading R4. Yeah, so actually, as you guys get into these more, there's lists, there's pages of lists of EQ, EQV, and it tells you exactly, in these cases, what it's supposed to do. And some of them, you'll notice they'll say unspecified. Which means that's the ever-popular implementation-dependent part. So whichever implementation of Scheme you're using may decide that they want to make that true or false, but it's unspecified in the language scheme. Generally, if something's unspecified, it would be better not to use that test, because your implementation of Scheme may print out true for something that's unspecified, and then you take it off to another version of Scheme, and all of a sudden your program isn't working the way you expect it to.
procedures? I mean, does it actually error out when it meets the procedure, or it just returns you some?
John's still reading.
So there's a test case, let me just put it up on the board. In this case, sorry.
Going over here. Oh, which one is it?
It's the lambda of x lambda y.
Okay. So it says equal question mark lambda xx lambda yy, which gives us the ever popular unspecified. In other words, all bets are off. So you guys can play with our implementation of scheme to see if there's anything that will do this. Maybe equal would work on this, but it is unspecified. So if you want to test to see if you have the same procedure, to see if something like this has been done, if something's been bound to the primitive plus or cons, then you would use EQ to see if it's pointing at the same procedure. Okay, so that would work if you're pointing at the same thing. So even if you defined, let's say that we define square of x to be times xx, and then we define rather power 2 to be square, then would power 2 and square be EQ? Yes, no, maybe? Are they going to be pointing to the same thing?
Yeah.
Well, this is bound to what this evaluates to. Okay, so this is going to be bound to the lambda returned there, so they will be EQ. They'll be pointing at the same object within scheme.
If you define power 2 as times xx, you would not be EQ?
Let's call this P2. So our square and P2 EQ. Well, actually, with EQ, it would be specified. Those are different objects. Different objects, plain and simple, boom. Okay, so that'll be false, and that'll be true. They're different objects within scheme. They're not EQ.
So because we named them, it becomes false rather than unspecified?
No, the difference is that here, power 2 is bound to what square evaluates to. Okay, so this is going to be bound to what square evaluates to. So in other words, we'll see this with the environment model.
Right.
We'll see that a procedure object is created, and then this binding will actually point to the procedure object that's been created. And we'll see this, I believe the environment model is next Tuesday or Wednesday.
The difference between the two lambdas, though, and the P2 and square tests is that?
The difference is that when we evaluate this expression, there's another lambda object that's evaluated, and another lambda object is created. Again, we'll see this in the environment model. This is a different procedure that's made.
It's also EQ versus equal.
Right.
Oh.
This is EQ.
Well, but if that was EQ, wouldn't it still be unspecified with the two lambdas?
If this is going to be EQ, it won't be unspecified. It'll just be false.
Really?
Yep. Because they're different procedures, they're different objects. It's just like creating new box and pointer structure.
Okay.
We create a new procedure, it's a new structure, new symbols, new something within the scheme.
Under the two definitions, would EQ question mark power 2 star XX be true?
Well, if we were to write that, what's going to happen in scheme? It's going to give us an unbound variable on x, or we may end up having x defined somewhere in the environment. Let's say it was 3. Then we're testing to see if power 2 is equal to 9, or we'd get an error on an unbound variable. Because remember, what scheme is going to do is it needs to evaluate the parts of the sub-expression in any order. and it's going to go to evaluate that sub-expression, and it's either going to not find an x that's bound, or it will find an x and it'll evaluate some number. Then we're checking to see if some procedure is EQ to a number, and that will return false.
But what if that was lambda x star?
Are they the same object? No. This is going to create a new procedure object. Okay. Lambda creates a new procedure. Every time we execute a lambda, there's a new procedure created. So these are going to be different, and that will be false. Some of the stuff with the procedures will be clearer to see when we do get into the environment model. We'll see exactly how we represent them.
Equation EQ question mark of square x and star xx.
It's going to be the same thing, because all we're doing is replacing the name.
Even though the first expression is the same.
Well, first of all, we could substitute any variable in for that. It doesn't care that it's the same thing. But it has created a lambda object or procedure object within scheme with the evaluation of square. And when we evaluate this lambda, there's a second object created. Okay, so there are two different objects, which means they will not be EQ. If they're two different objects, they're not EQ, period. Lambda creates a new object every time. Okay? Just like list is going to create a new box and pointer diagram for us. Yes?
In this list there, if you observe the 3, you have an x and a y, and those are between the binds of 3, it wouldn't be equal either with them?
Okay, so what you would like is this to be x, this to be y, and for us to have defined x to be 3 and have defined y. Well, do I need to change my box and pointer diagrams at all if I do that? When I evaluate the list 1, 2, 3, we're going to evaluate the sub-expressions in any order. And x will evaluate to 3, and that will be actually what's in our box and pointer diagram. Now, if instead we did quote x, quote y, then my box and pointer diagrams would change. And I would have x here and the symbol y there. Okay? So remember, scheme does the evaluation before we apply. Other questions? Yes?
I'm not clear on how you differentiate between EQV and equal. Like, under what times you would use EQV versus equal.
So you would use EQV if you had lists of numbers, and you actually cared if you were looking at the same box and pointer diagram. So in this sense, if we were looking to see, I guess we could use equal then. Okay, actually, EQV would be a good one to use if we had these lists. EQV is just better to use with that. Do you have any sort of EQ is typically used to see if it's pointing to the same thing. But that's going to tell us the same pairs.
It's like EQV kind of has a built-in smart to distinguish between
Numbers and symbols, and EQ does not.
And equal has a built-in smart to distinguish. Assuming EQ, what matters to you is what's in the pairs rather than...
Right, but the question was between EQV and EQ, I believe, right? Or was it between
EQV
equal?
and equal.
Oh, okay. So this is, EQV is if you're looking to have the same box and pointer structure. If you want to have the same box of pointers, it's the same thing in scheme, meaning A and C over there. This is looking for if two things would print the same, which means A and B over there, C and B over there, A and C over there. Yeah.
So EQV has the functionality of EQ, but
In
with
terms
the
of pairs.
With the added feature that it
The
can
added
look at
smarts that it
numbers.
can use numbers.
Okay, so you can think of it as EQ with numbers.
Right.
Strings.
And in fact, EQ, when we had said before EQ on the list A and C, scheme actually knows if those are bound to the same thing. And it doesn't actually need to go through the list structure. They can just check the binding. Okay, so EQ, in that case, wasn't even looking at the box and pointer structures. It was just looking to see if the binding was the same. Okay, here we're actually looking at the box and pointer structure. Yep, no? Does it?
Yeah,
It just has the smarts for
yeah,
numbers.
you can think of EQV as EQ and equal and all the other kinds of equal that are data
Rolled up into
specific,
one.
where doing an exact object similarity test isn't what you want. For example, with numerical equals, you want 1.5 to be the same as 1.5, even though it might not exactly be the same as 1.5.
3.5 to be, 3 plus 5 to be the same as 8.
Yes.
Equal kind of thinks like I do.
Equal is the person's equal, yes.
Is string equal, if you use EQ on a string, how is string equal different from EQ?
They're different.
So string equal is another.
Yeah, we actually haven't really looked at strings at all. I mean, we've kind of used them a little bit in our displays. When we say display and then we put a string, we haven't really used strings much at all.
Okay, so
I haven't looked at that. But it's just a different type of equal. Actually, you can look, if you're really interested, you can look into the revised report, and it talks about all different tests for equalities, different types to see what, you can test to see what type. You can say number question mark. You can say pair question mark. There's different things you can ask to see what type it is for the data. And in fact, that's what EQV would be using. Because it would say, if it's a number question mark, then I want to use EQ, rather equals. And then, if it's a pair, I want to use EQ. And it's going to go through that chain, testing for each data type within EQV.
Under what circumstances do we need to know that the definition that A is not equal to B? You said that it's a good thing that...
Yes, it's a good thing. That was a while back. So why would we want to know if A and B are different or A and C are the same? Well, we haven't gotten there yet, but we're going to get to something called mutation. And we're going to actually be able to, rather than what we've been doing, where if we want to change an item in the list, we actually need to build up a new list structure that keeps some of the original elements and then the new elements we want to put in. We're going to see that there's a way to actually go in and destructively modify our lists. And we'll see that in about a week. So in that case, if you're going to go in and destructively modify a list, you may want to know, because if we're destructively modifying A, we're automatically doing C, but we're not doing B. Okay, so those are the cases where we're going to start to really want to differentiate whether we've got different structure or not. Check. All right. So given those tests, it's the eraser that likes to write as it goes. All right, so we have something in called memq, memv, and member. Okay, and the general behavior is that these take two lists, rather, let's look at one. Member is going to take a symbol, where the symbol could be something like Holly, and then say, I am Holly. Excuse me? No, these don't have question marks on them. No, these got different behaviors. So any of these, memq, memv, and member, it's going to take something here, symbol, and it's going to take a list. And what it's going to do is it's going to look for that symbol within the list. If it finds it, what it returns is the list that starts with that symbol and any remaining elements. So in this case, I only had nothing after Holly, but let's say I said member Holly is teaching. Then this is going to look for the symbol within this list. It will find it here, and it returns the list in which that is the car, which means it's going to return Holly is teaching. So this is a way to find if something is in a list. It only finds the first instance of it in the list, and it returns us the list that has that as the beginning of the list. Let's look at the box and pointer diagram. Okay, we can describe all the procedures as doing the same thing, but member uses equal, memv uses EQV, and memq uses EQ. Okay, so we can describe the behavior the same way, but the test for equality is different in each of these three things. Yeah, so we have a different way to test for equality. So we have some tests here. You look at page 3 of today's lecture notes. I have some examples. So we're going to test memq, C on the list A, B, C, D, E. What will this return? The list C, D, E. Okay, how about if we say memq F on the list A, B, C, D, E. Is F in the list? No. So it actually returned false. So let's say you're searching for something in a list. This would be a good way to do it. You search to see if something exists. If it returns false, you know it's not there. And if it returns true, you know that the first element of that returned list is what you were looking for. Okay, let's start to see where things get differentiated. memq 2.3, not a consel, but 2.3. In the list 2.4, 2.3, 5, 6. It may or may not work. Our system, it doesn't.
Wouldn't 2.3 be the symbol 2.3 instead of the number 2.3?
Yeah, it's a number.
Not if you put a quote mark in front.
There is no symbol 2.3. A number is a number, but we don't know how they're represented internally.
So it looks at the difference between the second line and the third line in terms of the list is if a symbol can't start with a number. So if something starts with a number, it becomes a. Why isn't that the symbol name 2.3?
Because it's obviously 2.3 inside building, right?
No, the question is, this is quoted. And I talked about before, if we quoted something, that we didn't evaluate anything inside of it. And numbers are numbers are numbers, and the quote doesn't stop those. Yes, everything I've now taught you is a lie.
So the things, if it starts with a letter, it'll become a symbol, and if it starts with a number, it will be a number. Is that
Sort of the way it goes, yeah. A number is a number is a number.
If you had B22,
So if we were
that
saying
would be a
something,
symbol, but if it was
so something like this, is what you're saying? Or if you're saying, if we said quote B22 to make a list like that, this is a symbol B, that's just a number. Numbers can't be symbols.
whereas the one above it would be a symbol.
That's a symbol, B22, because there's no
So
space.
if it contains a letter anywhere in the
Yeah, so if we wanted to have 22,
22B,
can we start we can't start a symbol with a number, so I'd have to go that way.
You can't start a symbol with a number?
No.
What's it going to do with the quote, the list full of things like 22B?
It's going to have problems.
It's just going to...
Well, just like we couldn't define a variable name to start with a number, a symbol has the same sort of naming convention. You couldn't do that.
error out or
I would assume it would give you an error.
okay.
So you couldn't do quote 2.3 either. Like if you actually wanted to search for the symbol to look like 2.3, there's no such thing.
It'll actually return the number 2.3. Quote of a number is a number.
Oh,
Okay.
but it lets
So
you do that.
you could quote a number. We usually don't. So we're using this as a nice, convenient way to write a list here, but yet all the numbers are numbers. They're not symbols.
So it is quoting each of those, but
Right, you can think of it as quoting each of it, but the quote of a number is a number. So this is where a quote goes. So we could either say this is false, or it would be really more correct to say that it's unspecified. The system in the lab should return false on this, though. It does return false on this. Okay. But what if we did an memv on the same example? It's going to return the list 2.356. Okay. Check. And remember, there's some more examples in here. You guys can run these on the computer if you want. What I'd like to talk about for the remainder of class today is why would we want to have symbols in the first place? So what we're going to do today is we're going to look at symbolic differentiation. Let's get myself some more words. So, you guys did differentiation in month 0? Oh yeah, lots and lots and lots. Well, we're going to look at some pretty simple stuff right now. We're going to look at the following rules for differentiation. Oh no, not 4 weeks ago. d dx c, if c is a constant. We're not going to be really doing much challenging differentiation here. Okay, then we're going to have dx over dx, 1, and dy dx, if x is not equal to y, 0. Looking sort of familiar? How about something a little bit harder? du plus chain rule? Oh, rather, sorry, I didn't do it. Thinking chain rule, thinking multiplication, right addition. Sorry about that. Now, let's do it. Okay, so here are some rules for differentiation. Now, given these rules for differentiation, I want to write a scheme system that's going to do differentiation. But I don't want it to try to evaluate any of the x's. I just want it, if I give it something like x plus y, and then I want to take that derivative, and actually since it's scheme, with respect to x, I want it to return, well, in the original system what it's going to return is plus du dx or dx dx, which is going to be, and then dy dx is 0. Okay. So, not in the original system. So if we look at page 4 of the notes, this has the deriv code on it. Okay. So we define deriv exponent expression variable. And do we want to write all this code up?
That x at the end of the deriv is
with respect to, right. So we define, let me write portions of this. We define the procedure deriv, and it takes an expression and a variable to derive with respect to. And then we've got a cond. Okay, so when we call deriv on plus xy, which statement under the cond was triggered? Well, you guys will look at the code, so I don't have to write it all up on the board. Is it a number? Is this a number? No. Is it a variable? Variable is just checking to see if we've got a symbol. Is it a sum? Well, a sum looks to see if we've got a pair, and if the car of that pair is plus. Okay, good. So we've hit that case. So that case says, if we've got a sum, what we want to do is we want to make sum of the deriv of the addend ex of the expression and then the deriv of the augend of the expression with respect to the variable. Okay, so this is what we're going to be doing. Okay, so these are some nice data abstractions. If I were to have a list that looked like this, draw the box and pointer, how would I pull out x? Okay, so the catter, so we could define the addend of x to be the catter of x. And how would we get what?
EXP?
Does it matter if we say exp? Does it matter if I say x, y, z, abc?
No.
This is just a procedure we've written, right? It's just a selector that takes something in. So we're applying that to x. X will be substituted in, but it can be anything we want. So similarly, how would we define augend, which in this case would pull out the y? I think I might have heard one too many D's there. It's the CADR, any case. CADDR. Okay. So that's going to pull that. So what we're going to do is we're going to do the derivative. This is going to be x with respect to the variable x. And then we'll do the derivative of y with respect to x. Okay. So make sum is a procedure, and all make sum does right now is make sum is defined as taking in two variables and making a list of plus with x and y. Okay. Which is why we're getting no simplification. Okay, because it's just stupidly banging a plus sign on front of those two things. But what if we wanted to do some smart simplification? What if we had two numbers and would like to add them? Now, if we had something, if we were trying to add, say, x plus 2, we couldn't simplify it. But if we're trying to add 1 and 0, we can. Okay, so let's do simplification where we can. What we'll do is we're going to redefine make sum. Well, we're not going to redefine how many parameters it takes, because that would be breaking some abstraction rules. We don't want to change our constructors or our selectors on our users. This is what we saw when we did the game of 21. Okay, we added something more to the data structure, but we left the original selectors the same. They returned the same thing that they were expecting to be returned the first time, which is why it didn't break the system when you guys rewrote the data structure. Yeah. We saw some simplification when we were looking at rational numbers. Right? Do you guys recall when we had the constructor for rational numbers, we looked for the GCD of the numbers? Okay. What we can do in this case is we can have a cond. Okay, and what we can say is equals number question mark. This is not a primitive. This would need to be defined. So what we're going to do is we're going to define equal number question mark is going to take an expression and a number. And what it's going to do is it's going to return the and of a test to see if the expression first is a number. And then if it is a number, is it equal to the expression? Why would I want to check that I have a number before I check for the equal? We don't want to do that on things that aren't numbers. Okay? Remember, and is a special form that's going to just evaluate each of the expressions in order, and as soon as it hits one that's false, it's going to bail out. Okay, so if it's not a number, we don't even go to check the equal sign. So we prevent ourselves from having any errors by doing it in that order. So if x is a number equal to 0, what would we want to return? Well, we're trying to put together x and y added, right? So if x is 0, y. Similarly, if y is equal to a 0, then x. Okay. The next thing that we're going to do is we're going to say, well, is x a number and is y a number? If x is a number and y is a number, what would we like to do?
Plus xy.
Right, we're going to actually return the value of adding those numbers. Finally, if we don't hit any of these cases, what are we going to return? Okay, we want to return plus xy, but we want to actually return the list of the symbol plus with x and y.
Why do you need your 0 tests if you also go on to do your...
Excellent question. Why are we doing these?
Because x may not be a number in the first case, or y may not be a number in the second.
And you can't add a symbol to a number.
Those are handling cases like plus x0. Okay, so those are handling cases where one of the symbols is 0, but the other one is still there. And then this is handling where we've got two numbers, and if we haven't fallen those cases, all we can do is return the list. Okay.
Would there have been a way to expand this to any number of terms? Because right now this is limited to addition of 2 terms, right?
Make sum only makes addition of 2 terms, sure. We could do pluses of pluses of pluses of pluses. And it won't be the simplest way, perhaps, of simplifying, because we may end up...
You could even redefine...
Would it be a recursive to handle more terms, or no?
Yeah,
Well, I mean, so basically it's going to call deriv on the addend and the augend. So if we had a sum, that was plus x2 plus x3, we would come in here and then we would call to get the derivative of this. And what that would do is pull the derivatives of these. Okay, so it's going to be a recursive call. So we can do derivatives of sums of sums of sums. What we can't have in this system is something that looks like that.
Right.
Okay, so we only have each addition is only for a pair, but we can certainly simulate that by adding x to adding y and z together. Okay. So we can simulate it in our system, although we can't write it what you would maybe go for the simpler case of writing it that way.
You can even change your system to take the operands in normal mathematical order. And then
Aha!
you just,
Excellent.
run into this problem.
Well, we'd still want to have some sort of a breakpoint for our recursion, right? So we wouldn't want to just have infinite lists. But what we could do is we could have x plus y plus z. If I wanted to change my symbolic differentiation symbol to take in things of this form, what would I need to do? We need to change addend, augend, and one more. Okay, so let's say we've had a list. This is our prior data structure. It was a list of 3 elements, plus, and then whatever x evaluated to, whatever y evaluated to. And now we're going to change it to this. Still a list of 3 elements. In this case, we're going to have whatever x evaluates to, then a plus, and then whatever y evaluates to. So how would I change make sum? Would I change any of this number stuff?
It's just the result at the end.
X, quote, plus y. Okay. That constructor's changed. If we change the constructors, we need to also change the selectors. So now the addend, instead of being the catter, is going to be what? The car. And the augend, still the same. Okay. So by making those 2 small changes,
We also need to change some.
okay, right. Do we need to change anything else? Well, that handles building it up and breaking it apart. But we also had a test. I believe the test was called sum question mark. Okay? So we have define sum question mark on x. And what that is currently testing, it says, is it a pair? And if it is a pair, is the car of x equal to the symbol plus? Okay, so what would I need to change in my test? I'm going to look at the catter of x instead. Okay. So now I've changed everything I need to change to get sum working properly. But our system is now confused a little bit, because now we're taking addition in infix and multiplication as prefix, which is a little bit broken. So what would we do to change multiplication? You guys got the code in front of you. The same sorts of things, right? So I find some space on the board here. So the routines for multiplication, the procedures are, we have define product of x, which checks and pair x, and then EQ car x, quote, times. And then we had define multiplier x to be the catter of x. We defined multiplicand of x to be the catter of x. And finally, we had make product. Let me write down the really stupid brain dead make product so that I can save my hand a little bit here. Make product on x and y returns the list of quote times x, y. Okay, this is the non-simplifying make product. The simplifying make product is at the very bottom of the page. Given these constructor selectors and tests, what do I need to change to make this infix instead of prefix?
Product, change car to catter.
That is true.
Catter to car. And alone, and change how you're outputting.
Thus, all is done. Yes?
So when you're putting variables into this, or when you're putting values into this deriv, you can leave a variable in it. Like you can leave the y, and it will do its thing accordingly, right? Like,
Well, when we pass, so what you're asking is, what we call deriv.
like if you give
Let's say I call deriv on, plus x, y. I believe this is the same example I gave before. So yes, this quote applies here and here. So x and y are not going to be evaluated. So if we were to do something that actually might keep it around a little bit longer.
Deriv on plus 2, 3, is it going to return 0? I'm confused. Are we supposed to be entering values into those x's and y's if we want, and leaving them variables if we want?
It's symbolic differentiation. So the numbers are numbers, but the symbols, the variables, will be symbols.
Okay, and this is going to give us the right answer, right? This is going to say 0.
Well, when we go to look here, what we're going to do is we say, okay, this is a sum. So I'm going to make the sum of the result of differentiating
That
with respect to x, which is going to be 0. Then I'm looking at 3 with respect to x, which is going to be 0. And if I'm using my simplification, then it's going to actually hit here and return 0 there.
Okay, so I understand why it works when we leave one variable in there. It's the way we've always, I mean, it follows the rules that we know work for differentiation, right? It'll keep the y and
Right.
whatever. But I don't understand. I guess the rule of dy over dx equals 0. If we have two variables, I guess I don't understand that rule. Is what it comes in. But if we have
If you-
x and y in there, isn't that more complex? Like if I had to differentiate that, I'd have to move all my y over.
Implicit differentiation.
Y can't be a function of x.
So if we're differentiating y, you can't.
So is that rule?
Y with respect to x is 0. I mean, it's just.
Is that rule the same as?
That has nothing to do with the implicit differentiation and stuff that we did.
You're saying y is a constant number, like 7 or 8?
No. No, as long as y is not not as long as y is not an x.
Y is not an
Y can't
expression.
be a function of x.
Y cannot be an expression.
So y is not the independent variable in this equation or whatever. It's
X's.
some thing.
It's just some variable
Not
which.
a function of x.
Right. Right.
So that's not the same as saying it ends up being a constant. I mean, as far as this expression is concerned.
With respect to x.
With respect to x, it is a constant, I
Okay,
guess.
so,
Yeah.
So as long as I can think of those two rules.
Sure. You can collapse those if you want.
Similar, then I'm happy. Okay.
Okay. Yes.
I had two basic questions. In product question mark, the x, how can you, is that the pair UV?
It may be a pair, or it may be not a pair testing there. We don't know what it is. So we're just checking. Something goes in here. The first thing we do is we say, is it a pair? So product could be called on anything. We could call product on the number 2. And we're going to go in here. We're going to say 2 is not a pair. Bye-bye. I'm out of here.
Okay, I just wondered, my problem is when I look at this code, I can't tell, like, why you're asking whether it's a pair, other than I see the duv dx over there, and then I figure, oh, well, that must be why.
Okay, when we're asking if it's a pair, that's really just saying, is there any list structure? Are there any box and pointer diagrams? Because remember, if we have a product, it's going to look like this. And actually, depending on which representation we're using, it's either going to be times x and y or x and times. Okay, so we're asking if it's a pair, because what we want to know is there some sort of pair structure there? Is there a box and pointer diagram? Because if there is no pair structure there, I do not want to do that.
Okay, so some of this code handles if it's not a pair.
Well, basically, if it's not a pair, it's not a product. If we have no list, we have no product, because a product has to be a list, either in the first case, started with a time sign, or in our infix notation, that has a time sign in the center position.
Okay.
But it has to be a list if it's a product.
Okay. So my second question is, what is the meaning of the list at the end of both the make sum and product?
What is the meaning of list?
What's why or this quote?
At the end of the other one.
Other one. This one here? Okay, well, what we're doing is we're making a sum. This is our constructor. Okay, this is how we're making a sum. And it's very basic. A sum is going to be a list of two things. Or in infix, x plus y. Okay, this was the second way we wrote the system, but let's just look at the first one. Okay.
So a line above it is 11 together, doesn't it?
Right, that's going to add them together. But let's say that x and y were not numbers. let's say x and y were actually symbols, and to make those sort of stand out from that, let's call that variable b and c. Okay, so if the symbols b and c were what would pass in for x and y, this fails, this fails, this fails, we can't do any simplification. So what we do is we need to return their sum, and the sum is represented as a list made up of the symbol plus, and then this in this case would be b and c. Okay, so it's very similar to what we were doing with the rationals. Okay, like we had make rat, where we cons two numbers together. In this case, we're making a sum, and we're making a list of the plus with the two elements that we passed in, if we have no ability to do any simplification. Okay.
What would happen if you passed a pair to product instead of a list? Would catter die horribly, or?
5 times.
So a console, you mean?
Yeah, yeah. And
Okay,
it's 2
whatever.
and 3. If I pass that in there, will catter be nice and return nil, or will it say that's not possible?
Well, what's the cdr of this cell? 3. It's going to happen when you say car of 3.
But does catter actually do it that way, or is there some sort of smarter thing going on inside? No, because
No, because it is a pair. It's a console. Well, first of all, let me just say that given our derivative system, unless we've added something to the system which does things horribly wrong,
right,
that's not going to happen.
But just in terms of
But if we did actually call product on that, it is going to be a pair, and we are going to look for the car of the cdr. The cdr is 3. We look for the car, and scheme goes, I don't even know what you mean to say car of 3. It's not defined. Bye-bye. You're in error loops now. And you're in the happy little debugger with happy little stickman in the happy little debugger. Any case. Yeah. Yes.
So in the simplifying smart make product and make sum,
Yep.
the reason we have to have a separate make product and make sum is basically we can't unquote our operator. Is that right?
Right. Remember, when we have quote times, or we have quote plus, those are just symbols. The symbol for the plus sign, the symbol for the asterisk. They are no longer operators. They're not operators. We can't use them. We can't apply them.
If we had a general way to turn a symbol operator back into its real operator, we could have one thing that did both of this, right? Both the smart simplifier make result or something.
We could make the and line there into an if statement with if the operator is plus, then you do that, or
Well, that's still this way. That's still splitting it. But if we could just generally
Maybe, but we can't.
is that applied?
No, because it's a symbol now.
the symbol plus has absolutely no connection to
The procedure plus. So it's separate.
So what's sitting in the car of the box and pointer? Is it plus or quote plus?
Okay, so here this is a little bit weird because I put x and y here. This would actually be the value of x and the value of y. And that would actually be the symbol plus.
Which we notate as a quote plus, or we don't need to keep it?
Well, if you were to build a list, let's say we said list of plus and times. If we were to draw that box and pointer diagram out, this would actually be the prim proc plus. And this would be the prim proc times. So by denoting it just plus, then it's the symbol. Other questions? Yes?
You could do something to answer the question about using the operators themselves. You could do something that will foreshadow what we'll see later on, which is instead of using the symbols plus and times, you could use the symbols make sum and make product. If you did that, what you would end up generating is something that looks very much like a scheme expression that would, if you could just run it, do exactly what you want it to do.
Okay, right.
So in a sense, you'd be creating new scheme expressions. And we'll see later on in the course when we talk, and then here what we have is in effect an evaluator for those scheme expressions. And we'll see later on when we talk about how scheme expressions are themselves evaluated. We'll see exactly how that happens.
Other questions? Yes.
I don't see how in this case, in our cases where we are the only ones calling make sum or make product, there can be non-numbers coming in.
Certainly there would be non-numbers coming in. There'd be symbols coming in.
But wouldn't we be would that be a make sum calling a make product calling a make sum and eventually looking at the return values of the
Because-
purely ones and zeros?
Because right now our system doesn't have any any kind of derivative that returns anything other than a number.
No, we do. We have, okay, yeah, now we don't. I'm sorry. We do if you look at the 5th page where I added something into the system. So let's actually, if you guys want, we can do that extra rule. Let's do one more rule. So we actually have something that returns some symbols. So we're going to add to deriv the following rule. du to the n over dx is n u n minus 1 du dx. Okay, so how would I add this to my system? Well, we'd need to have some test, some constructor, and some selectors. Let's call our test exponentiation. So the way we're going to denote an exponentiation, well, the first thing we do is we need to check to see if we have a pair. Okay, and then if we do have a pair, if the car of x, I'm going to be doing this in prefix. That's what I wrote it here for. Obviously, we could change it over to infix just by making a few changes. And then multiply, have 2 asterisks as a symbol to denote exponentiation in our system. So if I wanted to get the derivative of x squared, I would write it this way. Just some symbol to denote exponentiation. Use whatever you want. Okay, so this is going to test. Now I need to have something to pull out the base, which is going to be, well, I haven't given you guys the structure yet, have I? Makes it a little bit hard to write the selectors. This is going to be the symbol. This is going to be the base. This is going to be the exponent. So what would base be defined as? Cater x. And define, I call it exponent. Exponent. And the exponent will be the, yeah, whatever we haven't been able to pronounce the entire lecture. Okay, so those are my selectors, and I've got my test. So now I need to build my constructor. Okay, there's a couple of things we should use as simplifications. One is that if we have b to the 0, we should return, and if we have b to the 1, b. So let's add those into our system. So cond
Exponent 0. 1.
Okay, otherwise, list, I hear list. The symbol for exponentiation. Then x and y. We're almost done. We've written our test. We've written our constructors and our constructor, our selectors. So one more thing I need to do. If I just wrote this stuff, would we have added exponentiation to deriv? No, because what did we forget to do? Actually add it to deriv. Okay, so we need to put our test into part of deriv. So the full deriv is on page 5 of today's handout. So what I'd like to do is say define deriv exp variable cons, lots of stuff. Okay, we need to add a clause to our cons. What are we going to add? Remember, we're checking if it's a number. The first one says, is it a number? Then we've got a test for a variable. Then we got some more tests. So we want to add another test in here. What's our test for exponentiation? Exponentiation, question mark. What are we checking to see if it's an exponentiation? The expression. Okay, if we do have an exponentiation, what do we want to do? Well, this is what we need to do. Okay, I hear make product.
No, make exponent.
And I hear make product. Do I hear make products? Okay, so I'm going to make a product. And what am I making a product of? Okay, so first thing is the exponent of the expression. In that rule, n, bringing the n down. So that's n times, now I need u to the n minus 1 times du dx. Okay, I got two more things I need to multiply. Make product only takes two things. So what do I want to do? Make another product. Okay, so we're going to make another product. With the first thing being what? Make exponentiation. And this is why you want to name things nice short things. There we go. Make exponentiation. Of what? What are the two things we're passing? Yeah, sorry. Other way around. Just listening to the audience. Okay. So there's our make exponentiation. One more thing to do. Du dx. The derivative of the base with respect to the variable. Called deriv on the base of the expression with respect to there. 1, 2, yes?
You can't actually do minus exponent x there. You have to create its own. Unless you know that exponent is a number.
I made the assumption that we had a number. And in fact, we made over here the assumption that we had the number. Okay. So as opposed to x to the y or x to the whatever, I made the assumption that the exponent was going to be a number. Okay, and that shows up here because if I had symbols, I wouldn't have wanted to use the equal number test on them. So it's a simple. So if you guys wanted to extend the system, you could make it more general by, instead of requiring that this exponent be a number, you could change it so that you could have it be a symbol or a number.
Which then everything becomes more complicated.
Yes. Yes.
You can't just-
This simplification, assuming that it's a number, makes it a lot easier for us to do it. Okay?
Or we could check and say unknown expression, check them the derivative maker by saying we're going to sheet A if
Right. We could,
and we don't have a numerical.
sure. We could actually change our test for exponentiation to make sure that the exponentiation is going to be times some variable or some symbol and some number. How would we change our test for exponentiation?
We'd ask is a number, is space a number? I'm sorry, is exponent a number?
Okay, so we're going to add one more thing to our and here. So we're going to check if we have a pair. Still going to check to see if the car is that. And then what we can say is number question mark the exponent of x. Okay? And that's going to require that n is a number. Okay, so we won't fall into a case where we're trying to do x to the y and we fall into here and we run into some sort of errors. Okay? And then you could add your system to do symbolic differentiation with actually having a symbol or a variable as the exponent. Any more questions? Okay, that's all for today.